Welcome to Composites Modeling using numerical methods. Today we'll be covering Module 7, Failure Theories. And I have invited Mr. Wei, who is going to guide us to another tutorial. In today's lecture, we'll be talking about a general overview of composite failure theories, and we'll demonstrate the design of a structure, fairly simple, using these failure theories. What are the consequences of failure? So matrix cracking and delamination are failure modes associated with resin failure modes, and they tend to be usually the weakest link of the composite system. When matrix cracking occurs, it is possible for the composite structure to carry additional load through the fibers. In the presence of bending, however, delamination can be detrimental failure mode. As you can see here, there's a resin cracking over here, a vertical crack that turns into a delamination. Here you can see several delamination planes, and in addition, you can see fiber failure. If we look at the different fiber failure modes that you could have, that could be fiber kinking, or in this case, what fiber kinking is, initially the fibers may be straight, and then after some amount of loading, the imperfections could cause misalignments, which could then get worsened as the load is applied. And you can see that here, and on the right, you can see the results of fiber kinking. Fiber failure can also occur due to tension when the fiber strength, is exceeded. And then you have fiber failure due to compression and bending loads that could occur due to wavy fibers, for example, under compression. Or it could occur because the compression strength is also exceeded. You could also have matrix cracking on its own, or the fiber could debond from the matrix. There's a lot of different many failure criteria exist, but the criterion will not always work for all cases. It is important to realize that we need to measure the strength at the lamina level to be able to use some of these theories that I'll be discussing. Here, what I'm showing you is a top view of the lamina, and the lines that you see here are fibers aligned along the loading direction. And I had discussed in the video link below, I'll be posting a link that shows the ASTM standards that are required to get some of these strengths. But for now, I'll go straight to each of these nomenclatures. Along the axial direction, in a unidirectional lamina, XT represents the tensile strength in the X direction along the fibers. And then YT represents the tensile strength across a fiber. There'll be matrix cracks, for example, could be caused by a load transverse to the fibers because the resin is getting exercised. On the right here, I'm showing the same plots than those on the left, but in the opposite direction. So a compression load will cause compression failure, XC, along the X direction. And then the matrix under compression can also fail. You can see that here. We'll call that YC. And then the in-plane shear load could also occur, and that is denoted by S in this particular scenario. There's a lot of different failure criterion in composites. There's the interactive failure criteria, which does not differentiate among different intralaminar failure modes. And the intralaminar failure modes could be fiber failure, matrix cracking, fiber to matrix debonding. And examples of this type of failure criteria will be Tsai-Hill and Tsai-Wu, which I'll be showing in a minute. And then you have the non-interactive failure criteria, which also does not differentiate between the failure amongst the intralaminar failure modes. And those examples are maximum strain and maximum stress, which I'll also show. And there's more advanced theories, interactive failure criteria for each failure mode. And in this case, you will have a failure mode for fiber failure alone, one for matrix cracking, and so forth. And then you have a more deeper based theory, which is a micromechanics based failure criteria. In this case, you can distinguish the failure modes. You're analyzing the structures at the micromechanics level to then be able to determine if failure will occur. Here, what I'm showing is a very simple theory. It's called the maximum stress theory. And you can see that if the stress along the fiber direction is less than the strength in the tensile strength in the tensile direction, in the X direction of the composite, where the fibers are aligned. In this case, the failure does not occur. And the same thing for compression, and then for the matrix as well. Maximum strain theory is going to use a strain allowable of the lamina along the fiber direction to then determine if fiber failure will occur. This in tension, this in compression, and also you'll have the same formulas for matrix, but now transverse to the fibers. Again, we're looking at unidirectionals, but this can also apply for plane weave. Tsai-Hill failure theory is an interactive failure theory because it combines multiple stress directions. Here, sigma 1,1 is a stress along the one direction of the lamina, along the fibers. Sigma 2,2 will be this stress transverse to the one direction, which could be fibers if it's plane weave, but if it's unidirectional, that'll be matrix dominated property. Sigma 1,2 is the in-plane stresses, and then X, Y, and S are the strengths of the composite, which depend upon how the stress is. If the stress is positive, then XT will be chosen for X. And then if X sigma 1,1 is less than 0, then XC will be the one chosen, and so forth. You also have the Aziz Tsai-Hill criteria, which is essentially the same thing as Tsai-Hill theory, except the absolute value of the cross product term is taken. So you can see here, this term will have an absolute value. Other than that, there's no difference in the theories. And then there'll be differences in the results between the two failure criteria only when sigma 1,1 and sigma 2,2 have opposite signs. Here what I'm showing is Tsai-Wu failure theory. The Tsai-Wu failure criterion requires that this formula be less than 1. And here F1, F2, F11, F22, F6, F12 are defined here at the bottom. And they all depend on the various strengths that you provide. You also have this F12 term, which is a cross term, and that cross term accounts for the biaxiality of the system. And sigma biaxial here is the equibiaxial stress at failure. So if that value is known, then you can use this formula. On the other hand, if this value is not known, in industry, you will see the F12 is chosen as F star squared root of F11 and F22. And in a lot of cases, this F star is chosen to be between 0 and 1. In most cases, you will have it as 0 if it's not known. But you can do a sensitivity study. What is a Feynman procedure? So if you're given loads and boundary conditions to the problem, what we're after is to determine when the structure will fail. And to do that, as you see, we need to get the lamina stresses in each of the layers along the material principal directions. What do I mean? We need to get the stresses along the fiber directions, transverse to the fiber directions, and that's required because, as you can see, we have these various strengths which are then used in each of these criteria. And so what is the software doing? Is using the ABD matrix, which we discussed, is trying to solve complex partial differential equations for the problem, and it will use a discretization method where we divide the domain into small elements, into some finite number of elements. Those elements are connected by nodes, and these three equations will be solved using linear algebra. We're here in this example, we're showing that the solver will solve for the deflections U naught, V naught, and W naught. These are the deflections at the mid-surface. Those deflections then can be used to get the strains at the mid-surface, and then it can be used to get the curvatures of the system. And if you have these two information, now I can get the strains in the global direction for every layer using this formula. And you can see this varies as a function of location of the ply, where Z is the distance from the mid-surface to the ply location. So this allows us to get the strains. The strains will have to be transformed because it's in the global orientation. We'll have to transform it using this transformation matrix, where the transformation matrix is given here on the right. Alpha is a ply angle. M is the cosine of alpha. N is the sine of alpha. This multiplication allows us to get the strains that I need in the material principal directions. These strains at that particular ply can then be used to determine the stresses at each of the plies in the material principal directions, where Q is a stiffness matrix that relates the stresses to the strains. And we have a whole video in lecture 4 that goes into this formulation specifically. So we're going to jump to an example. I'm going to tackle IM 7977-3. The mechanical properties are provided here. And these are just estimates. In a design process, you will have testing that will allow you to determine the moduli of and the mechanical properties of the lamina. And I showed you in lecture 2, the composite series, what ASTM standards are required to achieve that. We're going to assume a ply thickness of 0.009 inch. And then here on the right side, I provide various strengths. And those strengths can be determined from ASTM standards. They're provided here as an estimate. And we're going to assume that this is a primary structure that's fairly critical. And so we're going to use the A-Basis statistical strengths in the design process. I discussed in lecture 2 also how to estimate the statistical value, which allows you to ensure that over the life of the fleet, your strengths are robust enough in the design process. So this corresponds to the very strengths I discussed earlier. And then in terms of strains, they're provided here at the bottom as well. So we're going to study a wing model, and we're going to say the 0-degree direction for the global orientation, the 0-degree reference axis, that's going to be aligned with the flow direction. And then the stacking sequence for the system is provided as 90, 60, minus 60, 0, and that's the stacking sequence we'll be discussing. And then here's the top view of the system. We're going to assume this wing is fixed on this side. We're not simulating the rest of the airplane, but this is just an exemplar on how we could calculate failure indices using a software. We're only going to apply pressure at the bottom of the wing, representing the lift conditions of that wing. And so the question becomes, if I were to apply a pressure that's uniform, which we know is not uniform, has a parabolic distribution typically, or similar to parabolic distribution. But again, this is just a simplification of the problem to try to convey a study on how we can determine the failure indices. So the question becomes, what is the highest pressure that needs to be applied uniformly at which any of the failure indices becomes 1. Because if it becomes 1, that's when failure occurs. And when I say failure indices, what I'm talking about here is Tsai-Wu, for example, has this criteria. If it achieves 1, then the very first ply could fail. And that's called first ply theory. We're not saying the whole laminate fails, but in this assumption, we are. As is Tsai-Hill, the failure index for that, if it achieves 1, then that's when failure occurs as well. Now, again, that's an assumption. If the first ply fails, it's possible for the composite to take additional load, but we're going to assume that the whole laminate fails, and that'll be a conservative design. Tsai-Hill failure theory, the same way. If this achieves 1, then failure is predicted. And then for the maximum stress theory, if any of these criteria is achieved, then failure is also predicted. So now what I'm going to do, I'm going to pass it to Mr. Wei, who is going to guide us through this software portion on the modeling of this structure, so that we can learn how to determine the failure indices and determine which of the failure indices drives the design, what pressure is required to fail this particular design. And so now I'll pass it over to Mr. Wei. Thank you, Mr. Wei.
Hey everyone, this video will simulate a wing under the load, under the pressure at the bottom, and check the highest pressure when any failure will happen. This wing is one side will be fixed. Then we will assign the composite material. The composite material information is listed here, and the failure information is also posted here. So we have the stress failure and the strain failure. Then the failure criteria, we will check whether this four failure criteria, like a stress strain failure or the Tsai-Hill failure theory, whether the criteria larger than 1. If it reaches 1, that means the failure will happen. If smaller than 1, that means the design is safe. Before we open the ABAQUS, we will first get the geometry from SolidWorks. So first we will import the geometry from SolidWorks. We click import, click part, and then we can import this .igs file. We just mark it as 3. Okay, that's fine. Then actually we just need half of this model. Then we can cut it. We want to cut it at the middle, so because at the middle point, the z coordinate is 0, so we can just cut by plane. We create a plane based on xy, then the offset is 0, so this is plane equipped. Then we can cut it. Oh, sorry. Then we can just draw a very large rectangular. Anyway, larger than this cross section. Then we want to cut like this way. Click OK. Then okay, this is the geometry we want. Okay, you can rotate it. See, the two ends is open, and we have a bottom and top and bottom. Okay. Then we can start to assign the material property. So this time we will use the elastic laminate material. The material information is listed here. So the E1 is 19 on MI side. So we just implement 19 power 6. We want to make the unit is pounds and the length unit is an inch. And the E2 is 1.36. Then it's 0.32, then 0.8 0.8, 0.4. Okay, that's done. Then besides this, we also need to input the stress failure criteria and the strain failure criteria. So click this sub points. Now I already created. So you can see when you open it, this one this is blank. Then you can just input all this information in. This two coefficients we just set as default. Default is 0. And then also the string one, you can input the string information in or list here. Okay. Then you click. Okay. Then next step, we will assign the material properties into it. Yeah, this part is what I assigned already. So you create a composite layout. Then total we have 8 layers. Then because it is symmetric, so we just only need to create 4 layers. And here shows the layer direction. We set like a 0 degree is along the like this spine direction. So here we just create 4 layers and then click this one to make it symmetric. The region will select all the region. Material just select what we created. Thickness is uniform. Each layer is 0.009. And then the rotation is 96, list here, 90, 60, negative 60, 0. And then all done. Click OK. Then we assemble it. Then go to step. We just create the general step, static step. And here I want to make the initial step and the maximum step default is 1. So here I want to make 0.05 and the total step is 1. So actually it will give us 20 total 20 steps. Then we can input a sort of large load. Then to check at which step the load the failure criteria will reach 1. And for the output, we first for the domain we choose the composite layout, and then here we just choose the material we just created. Then except the stress strain, we also need to click the failure this on, click this expand the failure fracture, and then you will find C failure measurement components. Then click this on. Then click OK. The next step, we go to the load. The boundary condition is simple. So at this edge, we just climb it. You can see. And then at the bottom parts, we apply the pressure. If you create, just choose this pressure. And then here I put 0.02 psi. Okay, then we go to the mesh. So for the mesh, I use the projected free mesh. And then generally I just simply set the global size is 5. That's good enough. And then I make the elements integration, full integration. Then we can run the job. So I already we can just rerun the job. Okay, from the monitor's output, you can see the increment will be 0.05 each time. Then there will be total 20 steps. Here, increment will be 0.05. Then here is the total time from 0.05 and then increase by 0.05 each time until it reaches 1. Then job will completed. Okay, it's finished. We can see the results. So first we go to common, okay, unit, okay. Then we first check the results. Go to the results section point. We click this envelope so that it will give us the maximum value. Then we will check the failure material one by one to see when it reaches 1. So we can see this 2 TS-AIW. Okay, it seems it's not reaches 1. And then I check this one. Okay, also not reaches 1. Then check this one, not. Check this one. Okay, it's not. So that means the load we set is kind of small. Then we can enlarge our load. So now I will tune it. Okay, then we just make a load used to be 0.02, then now we make it 0.05. I think it may reach the criteria because when we set 0.02, the failure is around 0.6 something, so we just kind of doubled. Okay, it's done. Then let's see the results. Okay, look at this. So that means in this Tsai-Hill failure theory, the fracture, the failure criteria already reaches more larger than 1. That means in this theory, that the total things is already larger than 1. Then we want to, that means the load is too large. So we just go back several steps to see at which step the number will smaller than 1. Okay, so that means at the 0.75 step, it become like a smaller than 1. Then we check other place. Okay, in this Tsai-Wu's theory, that the failure is also larger than 1. Then we just go back one step, another step. Okay, that means 0.65. At this step is satisfy both of these two theory. And then we check the maximum stress theory. Okay, that's good. Maximum strain theory. Okay, that's good. So that means at step 0.65, the load is good enough that no failure in this becomes is larger than 1 or reaches 1. Then we can calculate the load. So we know the total load is 0.05. Then at step 0.65, it reaches the criteria. Now the load is 0.05 total, multiply at which step, 0.65, equals, let me get the calculator, that will be 0.0, 325, if I'm right, yes, at this load. Okay. Then one more thing, if you don't understand what's the meaning of like this this is criteria, you can go to ABAQUS document. You can just input ABAQUS documents. You can just search on Google and then go to the ABAQUS analysis user menu 7.2.3 and scroll down the end. Then it will tells you in this section it just tells you the field string, field strat, what is the field strat, which is field string. And then for the output, you can click this ABAQUS standard output variable and identifier. Then you Control F, search the things you want to see, like what it means of TSAIH. That means that this failure measurement and also the other C failure measurements. What's the meaning of the other C failure measurements? Also listed here. Okay, that's all about this video. Thanks for watching.
Well, thank you, Mr. Wei. As you saw in the video, the ultimate pressure was calculated as 0.0325 psi. And that's when the failure indices, the most critical one became 1. I'll convert that to pounds force per feet squared. And as you know, the pressure is the lift pressure is proportional or is equal to the lift force divided by the span area of the wing, which is equal to 1/2 the density of air at the altitude of flight. V is the velocity of the airplane squared, and then you have the lift coefficient. We're going to assume a factor of safety 1.5 because we don't want to fly the design at the ultimate pressure. So we're going to take the ultimate pressure divided by 1.5 to then get a limit pressure of 3.1 pound force per foot squared. And so I'm using foot squared because the remaining calculations will be using units of foot. The model was performed in inches, however. So we'll assume that at 30,000 feet and an angle of attack of 0 degrees, the lift coefficient is 0.5. The density is calculated from tables as 0.0013. And then I'm using units of pound force, second squares divided by feet to the 4th. I can use now these values, and these may not be extremely accurate, but this is just an exemplar on how these calculations are made. You can plug these values into these formulas, the 3.1 as the limit pressure, and the velocity becomes 66 miles an hour. So this airplane, to be able to, that's the allowable velocity. If we go any higher, then we could get a negative margin of safety. Now notice as I go higher in altitude, the density drops. So then the velocity will have to be higher. And so this is the calculations, and I hope you enjoyed this particular tutorial as we continue to learn about composite design. Thank you for your time and your attention, and I hope you enjoyed your day.